continue with the second lecture by Luis Caffarelli on
regularity
theory.
Okay, thank you very much. Okay, so let me restart with the proof of this theorem, or I'll give you the main ideas. Okay. So let me explain this picture. So this picture corresponds to the first, the Georgy Lemma, right? Basically, what we have is so we have a stripping time, right, and space. So this is time, and we are fixing sort of a cylinder in space-time. So something like this and like this. Okay. And so this is a slice in time. And as you remember, the first lemma says that if I have that, so the function w in the discussion is the function, the red curve above the bottom line. So that's w. And then we will have w phi, which is the truncation. So w phi k is going to be w minus phi k. So we have w, which is the full picture, and w phi k, right, which is w minus phi k plus. So w phi k is the little pieces left above the level phi k. Okay, and so the lemma said that if the lemma of the Georgy is stationary, right? This is evolution. So this lemma, what it says is that sort of in the first, we want to go from this full cube, we want to go to a half a cube, let's say, or half a cylinder in space, and the second half in time. In other words, we want to go from here, we want to go, if we do the side, right, we want to go from half a time up to there, okay? And so we know in principle that the phi, that solution U is below, let's say, 0 and 2, or minus 2 and 0, and then we want to show that in the future, right, then the solution will be below in a smaller cube. Okay, in a smaller cube like this. So in a smaller cube like this, the solution will have gone down. Okay, and as in the case of the second order, this is an infinite iteration. In other words, I have an infinite family of cutoff, right, that converge geometrically, so these are that sort of converge geometrically to a final cutoff in the future, okay? And this cutoff will take place advancing in time. In other words, here we have sort of this infinite sequence of cutoffs that sort of makes the solution go down. Okay, and then cutting off in time simply will mean that you start with your energy inequality, which is like parabolic energy inequality. At times, the times decay will be converging to the time minus 1. Okay, in other words, we will. So basically, if we manage to do that, we will end up showing that if you start with a very tiny amount of mass. Oops, sorry. It's running out. It's running away. What happens here? This is one like far into the future. Okay, we are almost there. Okay, yeah. So I was saying then. So we'll see. So the cutoffs in time will come in naturally because we choose for starting time more and more advanced line. So let me see. So this is what we are going. We are going to we take the sequence of test functions, right? And that corresponds to cutting, well, the minimal surface example or the Georgy's example at different levels, okay? And we want to end up, after this infinite sequence, with the function being down a little bit, okay? So let's see more or less, let me go more or less through, with not too much detail, through the main steps, right? So we have W, which is smaller or equal than 0, right? It's below the upper level. This is between, in an interval of time between -2 and 0, let's say. And what our assumption is that W is below, in this case, -2, that is will be the bottom of floor, most of the time, okay? And so we want to show that, as I say here, if we succeed, we will end up lowering your function. And the difference with the stationary case, here you have all of a sudden a new problem, right? Because once you have under that situation, you want to renormalize and repeat the argument, okay? But when you renormalize, since the operator is non-local, so the operator, the interaction goes all the way to infinity, when I make of this little cube a cube of size 1, whatever outside was height 1 becomes higher, okay? And so when I start to repeat the argument, then sort of the bound I have on my function on the sides is going to will be increasing. Okay, so it'll be larger and larger, and so I have to be able to control the integral of the tails with this larger bound. Okay, so so basically what will happen is this, right? In the first step, right? In the first step, you know, I was at, let's say, some level 1, and I assume everything was below that. But then I cut to this piece, and I renormalize, and so this little piece now has become, this little piece has become a 1-1 thing. Okay. Now, if the solution goes down a lot, then it looks very good because I'm getting a very good Helder continuity. But if the solution goes back a lot, when I renormalize, the sides are going to go up a lot. Okay. And so what you have to do there is just pretend you don't know that and say, okay, if the thing goes down a lot, still I will pretend that I only know that I went up a little bit, an epsilon down, okay? So if I do the iterative scheme that way, the Helder continuity is not going to be that good, right? Because I'm gaining very little in each step, means it will be Helder with a very tiny exponent. But on the other hand, the growth I have on the side will be expanding as I raise it will be going very far away, right? Because when I do this rescaling, this goes a little bit and the bottom goes 1, so the scaling will grow very slowly. And that means, so it will be exponentially very slowly. It's going to be like distance to the epsilon, okay? And so if you choose that properly, that makes it converts to any S power, because the S Laplacians, right, or my kernels, which decay like the S Laplacians, right, decays also like a power, okay? So that one difficulty we'll have to do, or one thing we have to do, is make sure, so we will have to work, so the real picture we have to work with is the following. In other words, I'm going to look at the oscillation of the function here, and I'm going to bound at the same time as I iterate, right? I'm going to bound the growth of the kernel of the function when I dilate by some very small power of r, okay? And so in order to do that, all I need to do is to just don't think that my gain is very, very little related to epsilon, okay? So if I gain 1/2, I still will rescale like if it would have gain epsilon, okay? So if I do that, then the tail is always under control in two senses. First, it grows very slowly, and also it starts very far away from my initial cube. If you see here, that is 2 to the 1 over epsilon. So it is the distance where the tail starts will be always very far from the initial cube. So that will give me a very good control on the tails. So this is the first things I want to point out on the technique. Okay, so now let me say something about the energy inequality. So the energy inequality is the standard thing you do, for instance, when you do the heat equation, right? In other words, you write your equation. Your equation is Wt, right, equal to this integral Wt. So let me write it here, right? Oops. So your equation is Wt, W sub t of x and t, right, equal to the integral of W of yt minus W of xt dy, right? Times the kernel. Too many things. Times the kernel k of xy dy. Okay. And so like in the heat equation, right, you multiply by W, but you want to multiply by the truncation of W, so you multiply by W, in your case phi k, the ones that you are working at the time, right, here and here, phi k, and you integrate in space and time, right? So this is the way you do the energy inequality. In the less, okay, W phi, the phi is constant in time. So when you take derivative of W, in in the left, you can replace Wt by W phi sub t, right? Because when W phi is 0, doesn't matter what Wt is, it's W phi sub t, which is 0, right? And when it becomes positive, the derivative is the same, because phi is constant in time. Okay, so basically, on the left, you can replace Wt by W phi t, and so when you integrate, you end up with W phi square at the top minus W phi square at the bottom, right? And then you have on the right this expression you can symmetrize, right? In other words, you can change x by z all over here and subtract, and then you have a symmetric form. But notice that here you have c minus x, and if I change x by c and subtract there, here I will have x minus z. In other words, you don't get symmetrized, you really anti-symmetrize. In other words, you can put a minus here, right? And that's what in the heat equation you pass to the left and gives you the energy, the kinetic energy, right? In other words, this expression, if I symmetrize it, becomes this bilinear form with a minus, okay? And so if I want to have a full energy here, this part of the energy, so what is the full energy you get? Then about the t times, right, you just get the integral of I square at the end minus the beginning, okay? And then the other term that I pass to the left is this integral, right, that was the integral in time of the b, that is the bilinear form of W phi W, okay? And so you want to have the energy, so you write W as W minus phi plus W phi, and you end up, the good terms are these ones, or the energy terms are these ones, right? The integral at the last final time plus the bilinear form on phi, and on the right you have the initial phi, and then you have this term, okay? So that's basically the terms, okay? So let me discuss. So in the Georgy thing, you have the two steps. The first is that the energy controls the integral of phi square, right? And then the second step is that the integral of W square controls the energy, okay? So let's do the energy controls the, and remember there is no symmetric the control. In other words, the energy doesn't control just the L2 norm of the function, controls an LP norm which is bigger than 2, And that's what allows you to have these iteration processes that forces the solution to go to 0. Let me point out that there is this also this initial hypothesis that a 0, that at the first step the L2 norm has to be very small, right? In this case that we are working in time, that simply means that you have the minus, you are going from, let's say, -4 to 0, and then in the -4 in the interval previous to the next iteration, all you need is a slice of time where the integral of W squared is small because of the initial time when we do here, because of this initial time. So if this initial time is the A0 where you start in the Georgy process. Okay, so just one slide is good enough. Okay. So so we first check what the energy on the left controls, and the energy on the left, right, controls. The energy on the left includes the final t square, right, the final integral of t square. So it includes this integral, right. So the energy on the left controls the supremum of the L2 norm of W phi, because it's and controls controls an LP norm of W phi and controls the energy. So when you just by a Sobolev interpolation argument, you end up that the energy controls a power bigger than 2. Okay, so so the question is now how we can control. So we want now to go to the L2 norm, because this is the one we are going to use in iteration, and we want to show then that the energy controls something a little bit better, right, than the L2 norm. So the L2 norm, you write it as an L2 norm. This was the Georgy trick, and you don't forget the indicator function of the set where W phi is positive. Okay, so it looks like you have done nothing. Then you do Helder, right, and so you have a bigger power here, bigger power than 2, and then you are hanging this, and this, in principle, it looks like you don't have any information, but the idea is that you now refer to the previous phi. The previous phi was below. In other words, this phi now is going to be my phi k, and then I look at the phi k minus 1, and where W phi is bigger than 0, W phi k minus 1 is bigger than 2 to the minus k, because they are separated by a 2 to the minus k gap. Okay, and so that's where you use Chebyshev, right, and say this measure of the set where W phi k minus 1 is bigger than 2 to the minus k is smaller or equal than the norm, right, of W phi, the Q norm of W phi, times a large coefficient, right, with times 2 to the k, because we are going from 0 to 2 to the minus k, so that integral is like 2 to the minus k times something. So basically that's where you get the large exponent on the large 2 to the k exponent, but you get the growth which is sort of exponential. So basically this is what you get, and so let me after this computation, the good basic lemma then is the following, is that if W is less than the first step most of the time, then ends up being identically 0 after a while. Okay, it's this is the iteration. I'm just go this we discussed before. So you get that iteration, and if A0 was small enough, then you are okay. Okay, this is what I just discussed. Now, let me say about let me say about the control on EK, right? This is an important thing. So we had the bad terms on the. Now we want to control the energy by the L2, right? And so So we had the energy was one of the good terms, was the good term on the left, and then we were left with these terms. Okay. So we are left with the L2 norm, which is what we basically want to control with, okay? And then we have these two terms. So the first term, the first term, right? Okay, this is what I said, that you choose the smaller slice, right, in the past. That is the L2 control. You can do the L2 to take the better slice for you, which is the infimum over all the slices, and then that you can substitute by an average because it's the infimum. So you are substituting by an average, right, which is the previous AK minus 1. Okay. So we have this extra term, right, this cutoff term, which is the one that you have to deal with really. Okay, and so this cutoff, right, you write, this is just, that is what it is, a bilinear form, and so what you do is you do Helder 1/2, 1/2. In other words, you take the kernel, right, and that the kernel as the square of its 1/2, and then this with 1/2 of the kernel you do L2, and this and this piece here there is a minus missing. Sorry, there is a minus, right? This times this piece times the 1/2, you get another L2. Okay, and so when you do that, the L2 of the L2 of W, right, is basically the energy again. So you can take so you have A times B, you take a small multiple of A, so you take a small multiple of the energy, and that you absorb on the left, right, because we are controlling the energy by this quantity. And so basically you have to deal with this other term, the K of XY, and when you do this computation, right, this is the minus, then we have and here let me point out that we are keeping the characteristic function of WK bigger than 0, right? In other words, in the other inequality, we have the W and we have this cutoff, which is missing the minus. So this cutoff with the minus, we keep it with this extra term. And so if you do that, then you can show that since the phi k has this slow growth outside, and inside it has very little oscillation, then that you can integrate, and you are left then you can integrate in one of the variables, and then in the other variable, then you are left with the characteristic function of WK. So you are left with once more this term that we control by the previous step. Okay, so if you put all of that together, you end up with the so we are still a term missing, right? Which is so there is a term missing because when I do so, we have this term here. This term has WK and WK minus phi k minus. Okay, and so in this term, let me point out that in fact this term has a good sign because WK is positive, WK minus phi k is negative, and in the bilinear form they interacted in the two complementary sets. In other words, where W minus phi k is negative, WK is 0. And where when W is positive, W minus phi k is negative. So when you write the bilinear form, right, the bilinear form, right, has something like WK of X minus WK of Y times kernel, right, times, and then we'll have W minus phi minus of x minus w minus phi minus of y, right? But if this is non-zero in x, then this is 0 in x, right? And the other way around, if this is non-zero in y, then this is 0 in y. So really what you get is positive times negative, okay? So you get positive times negative, so positive times negative, right? And so you have, let's see, the bilinear form then is positive times negative. The bilinear form then is negative, and minus is a plus, and I'm getting the wrong sign. Let me see. So BWK W minus phi k. No, this is, it has the wrong sign. Let me go back. Okay. Yeah, here is the expression here. This is the sign. It has a positive sign on the right. Yeah. So on the right you have this. Yeah, here I am. Yeah, so it has a positive sign on the right, the B, and so and you have positive and negative. So you have negative on the right. When you pass to the other side, you have positive. So this term really, it helps you. We don't use it here, but we keep it for the second step. Okay. So basically, we, at the end of the day, right, we can go to the second step. So we have the first lemma that says if you start very little, then you disappear. And now the question is, if you start not so little, right, in other words, if you know that the function is below phi 0, let's say half of the time, or something that you can assert in any step, then you want to show that that still under those conditions the solution goes down after a finite number of steps. Okay. Now this, in the Georgy case, remember I was pointing out yesterday, is based on sort of the fact that if you have a function in H1, right, so you have this function which is in H1, and it is, let's say, between this constant 0 and 1. So you cut off, right? If you cut off like this, the H1 norm decreases because gradient here is 0 now instead of being 0. So it's still less. And so there is basically this idea that functions in H1 cannot have jump discontinuities. And so what the Georgy did, that they make that quantitative, and said, okay, if I have a function in H1, which is 0 in a non-trivial set and 1 in a non-trivial set, there must be some region in between where the function is going from 0 to 1. Okay, and so this is the estimate, the Georgy isoperimetric inequality that says that this area, this region in between, right, controls this region in between controls basically is controls by above some product of this area and this area. Okay. So in our case, right, if we are going to do that iteration, we are starting with the hypothesis that the function is already less than this value in a non-trivial region. Okay, let's say 1 over 10. Okay, so we are going to start by saying, okay, this region is at least 1 over 10, and then if this region is not below, and so here we are going to try to get the critical smallness of the first lemma, right? Because if we get the critical smallness of the first lemma, then we are done. We are staying strictly below my original thing. So here we go for the critical critical smallness. And here we start with the, let's say this with the existing smallness. You can always say, I think that my equation, my solution is half of the time below or half the time above. If it is half of the time below, you flip the equation, or you flip the function, right? So now our gain is that we have this mu that we can assert no matter what, and we have this delta, right, which is the critical amount. And so the idea of the Georgy, right, was this of cutting and rescaling, cutting and rescaling, and in a finite number of steps you will get to your critical. Okay? In other words, the second step is not an infinite process, it's a finite number of steps. In other words, you go half the way, and if you are not below delta, right, you repeat, and you have lost some piece, because delta is non-trivial and mu is non-trivial. And then you repeat, and if you still are not below delta, then you gain exactly the same amount, right? And so if you do that 20 times and you never went below delta above, then I mean you get by this inequality you get that the set has disappeared anyway. Okay, so basically, so this was the issue. Now, the problem that we have here is that this is true up to h1/2. In other words, the function cannot have a jump discontinuity if it is in h1/2 or above. Below h1/2, then you can have jump discontinuity. Jump discontinuity is there. Okay, so we need to find some other way to express what happens, right? And so we have to look, there is this term which was positive that we throw away in the first step, and this is what we are going to use now, because that term, in some sense, connects the positivity and the negative region of U, right? This was the...
The infinity is in space and time, right?
Yes.
This is going to be only space, step 2?
No, all it says space and time. This is going to use time heavily. Yes. The first one already was space and time, because you are cutting, and these two, yeah. No, it's everything is full. So, well, let me go back. They will appear there. Okay. So basically, the iteration process, let me go, this is a bit technical process, so let me go more or less light on it. So we will have 4 parameters, okay? Delta, as I wrote there, is the critical mass we want to go above. In other words, if the set, if you are, so delta is a small number, which is the amount that the solution can be there. I'm sorry, the delta is I think the delta here is the complement of this delta. Right? Let's check it in a minute, okay? So, and mu is what we can get, right? And so we will use a parameter lambda, which I'll tell you what it is in a second, which is much smaller than mu and delta. Okay, it's a large power, and these are numbers less than 1, okay? And then my final critical number will be a power of this lambda, which I'm going to call lambda star, okay? And then also I need to fix, I'll fix it at the end, but I think it's going to be clear that it is a constant that only depends on the numbers of steps I did. I'm going to fix the epsilon of the sides of the iteration, okay? So in other words, I'm going to fix an epsilon that makes 2 to the minus s over epsilon, right, where s is the power of the kernel, right, less than this lambda star square. And this number is like, that because it is the the kernel is 2 to is r to the minus s, right, and so this is, and the 2 to the 1 over epsilon comes from the growth of these wings on the side, okay? So, so basically what we will have is these 3 consecutive cutoffs, as I did here, right? So one will be if phi 0 is the bottom, is the normalized, renormalized bottom all the time, right? That is what corresponds to this cutoff in the Georgy case, 0. Then phi 2 corresponds sort of to the top in the Georgy case, right? And phi 1 is an intermediate kernel where we are going to take account of how our function w is crossing that level. In other words, we have a function, right? We will have that our function w goes from, as you evolve in time, right? Initially, our function w will have will be above phi 0 an amount related to the mu. In other words, will be below the phi 0 an amount related to the mu. Okay? And at the end of the time, we are going to, as time goes by, we want to see how much of w, right, crosses phi 2, okay, which is the top, right? And then here we have this intermediate region, which in the elliptic case, we just did all in one chunk, in one jump. But here, what we are going to do is we are going to advance in time and take some control on how going from in time phi 0 going to be below this level to time, final time to be above this level, how that function is crossing this intermediate cut. So we are going to show that the time and space that the function takes in crossing this intermediate cut is non-trivial. And therefore, that will be the loss or the gain that we'll have at the end of the day in phi 2. Okay? So this is this argument of taking, sort of keeping control on how, as you advance, or in fact will be retreating time, the graph of our function is crossing the level phi 1 is what replaces this the Georgy perimetric inequality. And so let me just, you have to go through it's not hard, but you have to go through the details. So just let me tell you what happens. Why do we work like that? Okay. The idea of the proof is, again, we start with the energy inequality as before, right? But we now look carefully at the term that we neglected before, which is this term, right? Which is the mix of so this is the set. This corresponds to the set where u is bigger than phi, or w. I don't know why I changed u. W is bigger than phi, and this is the set where w is smaller than phi. Okay, so these are two complementary sets, right? And this is a good thing about the non-local problems, is that the non-local kernels see everything. To get something with second order case, you have to go through much more delicate potentials. Here, our kernel, this has the right sign and is seen simultaneously, right? So this is really, we have to put it on the left and is controlled by the things on the right, right? In other words, originally I put it on the right, really goes to the left. It's controlled by the things on the right, so it's supposed to be small. And that says that there cannot be in any slice too much interaction between the positive and the negative part. If in a slice there is some positive chunk, the negative cannot be too big because it's being controlled by the right-hand side. Okay, so so now we concentrate in the intermediate cutoff, and we write the energy inequality. Okay, and now we have again to control this term. I'll go back to W sometimes, but U and W are the same. Okay, so basically we revisit this term, right? Where was this term that was at the end on the right? This term was always bad for us, right? But again, what we did before, we control it by the quadratic U phi. This is AB, and then we control it A square, B square, right? And this we can absorb on the left, right? And this term, so now I want to look at this, so we control on the right, and this term is smaller than the lambda square, right? the parameter lambda squared. Remember that this cutoff is at level lambda, right? Remember the definition of lambda was that we have the 3 cutoffs, right? Right, and this was at level 1, this was of size 1, this was of size lambda, and this was of size lambda squared. Okay, so basically the function 5 of the second cutoff oscillates of order lambda. Okay, so these terms are of order lambda, and this is of order lambda, and you have the indicator function of B1, so when you integrate you get that this second term is controlled by lambda squared in the nearby and 2 to the minus sigma epsilon from the part where y goes to the tail. X stays in the ball of radius 1. So only one of the variables goes to the tail and adds this. But we said that we are going to choose this, right? In fact, much smaller than lambda, right? It was the 2 minus sigma epsilon was at the end was going to be much smaller than was going to be like lambda star. So this is also absorbed here, and we get then that this quantity, right, is bounded by lambda squared. Okay. So basically, if you integrate now between T1 and T2, then we get that the integral of W squared between T1 and T2 plus our now discovered good term is less than lambda squared T1 minus T2. Okay, but these 3 quantities are all positive. Okay, and therefore they are increasing in T2. So this indicates that their derivative, right? So if you look at h of t, the integral from some fixed T1 to t, it satisfies that. So it's monotone in T2 because this is positive, so it's monotone in T2. These are positive, so that means that the derivative of this integral with respect to the parameter T2 is less than lambda squared. Okay? Because this is growing like, sorry, this is T2, right? So this is growing less than this linear function. In other words, what we get is that this quantity, the trace of, let's say, the W squared restricted to the intermediate value, right, is almost decreasing, right? Because lambda is remember lambda is going to be a very small parameter respect to mu and sigma. So basically what we have is that this mass is almost decreasing, right? And we are concerned that originally was very small, right? And by the time we have near the end, right, the function has crossed into a chunk into phi 2, which phi 2 was lambda above phi 1, right? Because we have this ratio, right? And so we have that we are advancing. We start with something which is down here a good chunk of the time. We are advancing, right? And at the end of the time, we are concerned that this chunk is going to be up here a good chunk of the time, right? So if it's up here, then that means that the W2 squared, right, is of order lambda squared, right? Because the W intermediate is you cut here, so you have this chunk, but you are cutting the function lambda below this level, right? So this is going to be of order lambda, and so the integral will be of order lambda squared. Okay, so basically we are starting that we are like that this quantity has become of lambda squared above, right? Originally was very, very small, right? So it took, when cross the intermediate level lambda, right? It took, something has to happen, and it cannot go there without giving a big trace, okay? And so this is, so basically you do in 2 steps. First, to see how many slices are the ones that where you are covering a good chunk of the intermediate value, okay? And I said, I mean, it's not a complicated computation, but I'm just not going to go in details, basically what you do is you remember, as I said, that your function is almost monotone, and at the end of the day, if it has not gone through the critical delta, that means that it is above the lambda square level, so it is lambda away from the intermediate level, and so when you come back, right, you end up proving this is when you did those computations, you can find this intermediate set where you cross in the set. So in terms of time, here it is. That gives you that there is when W2 is bigger than 0, there is this lambda gap, and that's just, let me go through it. Okay, but it's just the computation is not just. This is going to be possible. You can look at the paper. The computation is straightforward. It's not nothing particularly. It's just careful. Okay. So basically, then we can prove the oscillation theorem that says that W is C alpha in space and time in Rn times this interval minus 2. Okay. So basically, you apply the iteration and you get the result. Okay, so this is, sorry if I went far, but this is fast in the last, but this is a computation that you have to sit and check line by line. Yeah?
Why is it that you need the tails to grow at certain rates so you can integrate, but why is it that you need them to start growing far?
Pardon?
You said that you needed to start growing like far from the region where you're...
Well, first is if you do 2 to the minus, it comes not only that great slowly, but far. But also it appears in one of the steps, it appears, when I did the phi nearby, and the phi, let me see if I can, well, there was a time when I looking at this, how to control this term, and I got phi of x minus y times the kernel times the characteristic function of the set where W was bigger than something. So that part was bounded, and you have to integrate the other tail. And you want that to be, as you do the process, you want that to be smaller than the lambda, right? The lambda was being the cutoff. And so this lambda is evolving, and so what you want is, so you want to say that that integral is less than 2 to the minus s over epsilon, okay? And there, in the computation, not only you use that the thing grows like that, but also that it starts far, okay? But comes just from the cutoff, comes naturally, yeah. Okay. Okay, so that's that for the variational approach, and then the other thing I wanted to discuss is the similar theory for the fully nonlinear equations. And so I'm going on that, depending on how far, well, I have the afternoon. So on this, I'm going to discuss of the whole theory. So I'm going to look at non-local fully nonlinear equations. I'm going to say what we think is non-local fully nonlinear equations. And then the theory for fully nonlinear equations, as I said, in the second order term, right, has 2 big chunks, right? The first chunk is the Krylov-Safanov theorem, right? That gives you the Harnack inequality, and then you apply to first derivatives of the equation. So let me just make a quick review of that, right? I don't know if I did it before, if it's here. I think it's here. Oops. Yeah. So let me first do the discussion of the second order to see what we are pointing out, okay, and then we will discuss it. So basically, first here I'm not going to the parabolic problem. The people, Chen and W, which were students of mine, and other people have worked on the parabolic fully nonlinear equations. And so basically I'm going to look at the stationary, okay? So let me say first remind you what is the theory for the second order stationary, and that will direct us a little bit on what we do in the general. So in the second order stationary, right, you are looking at the function f of the square. You remember as a motivation I gave for this, I gave the optimal control or the and the Pucci extremal operators, right? So I gave that example yesterday, right, that you have a media and you want to optimize the shape of the media to maximize your probability of going out in a given direction. And basically we end up that we wanted to look at an equation of the following form. So you are giving a domain D, and some boundary data. Well, let's go to the domain different. Since D are derivatives. This is domain omega, right? And boundary data F as you want, right? And then you want to, you have a family of linear operators, right? Aij, Dij, right? So basically, you want to look, for instance, a family of interesting families when you look at all operators such that the matrix Aij is between two multiples of the identity. Okay, so we look at all Aij's, which are sort of identity less than the matrix Aij, less than the matrix 2 times the identity, let's say. Okay, and so basically you want to see, so you say, okay, let me cook all possible operators Aij of x, Dij of u. So look at operators Aij of x, Dij of Aij, let me put it sub x. Let me write it as Aij sub x, Dij of u equal to 0, let's say, in omega with boundary data f. Okay, and means sub x in the sense that for each x, I can choose any one of these operators. Okay. So I have sort of a large family of possible operators, right? And so there are all, this is basically all possible families of diffusions, and I want to find the diffusion process that is the choice of this Aij of x that will maximize the expectation of hitting a domain or having a payoff at the boundary or something like that. Okay? And I say that if you want to find this special function, let's call it u0, right? What you have to do, right, is, suppose we are in this case, what I have to do is you have to find a function u0 such that the following. I have u0, I compute it d squared of u, right? Then the d squared of u, from the d squared of u at every point x, right, I separate the positive and the negative eigenvalues. So this d squared of u, I have the positive eigenvalues, lambda 1, lambda k, bigger than 0, and the negative eigenvalues, lambda k plus 1, lambda n, smaller than 0, smaller or equal than 0, okay? And u0 has to satisfy this funny equation, which is that says that the sum of lambda j or lambda j positive plus 2 times the sum of lambda j, let me see, I'm going to write lambda j, no, the other way around, the lambda j negative plus 2 times the sum of lambda j positive has to be equal to 0. Okay. So this is a funny problem, right? Well, how are you going to find out? What is the way you can find out? Well, the fact, okay, so let me tell you why, if I find this, that is a solution to this problem, okay? The first observation is that Aij being between these two matrices is invariant under rotations. Okay, so the second thing is that if U satisfies this at every point, right, basically, if I take the system of coordinates of the eigenvalues, right, then the matrix is 2's and 1's in the diagonal, right? So it satisfies this constraint, okay? And then I say that if I put the 2 and the 1 right, that this function is a super solution for any of these equations. Okay? Because since here I am multiplying the positive eigenvalues by 2 and the negative eigenvalues by 0, if I put any other matrix, right, then I will multiply this by something less than 2 and this by something bigger than 2. So that means that this function will be negative, right, for all any matrix I put here. So that means that this function all of a sudden belongs to the set, is admissible, and is a super solution for all possible equations I can cook up. Okay? So what is remarkable is that in fact this function exists, and it is a C2 alpha function, and so it's a classical solution of this equation. Okay? So so in general, basically, fully nonlinear equations are lim subs of linear equations. Okay, in other words, you take the lim over one parameter and the sub over one parameter and the infimum of another of Aij. So now we say, so basically, fully nonlinear equations are solutions of so are equations of the form sub over alpha inf over beta of Aij of alpha beta of x. Okay. There are two special classes. One special class is when you only take inf or sub, right? So these are called Isaac's equations. Okay, and then I'm going to concentrate. Well, I'm going to go through both. I mean, so there are two special classes. One is what is an inf, only an inf, right, over alpha, let's say, of Aij sub alpha of x, dij of u. Okay? So, for instance, if you give me any function f of a matrix which is convex, right, if f of the square is convex, the square is a matrix, so it's really a function of matrices, right? So if you give me a function f which is convex, right, then you can take the tangent plane at every point, and this is a linear equation, right? Okay, so you have a function which is convex, and this is an equation on the square of u on the matrix. You take the tangent plane at every point, and this is a constant coefficient equations, right? Because the Aij becomes constant, okay? And if function is convex, that linear function is negative, right, for every other point, and coincides with the level f 0 at that point. So that means that if you have a convex function f of matrices, you can always express it as supremum of tangent planes, that is supremum of linear functions. Okay, so convex functions have the property that they are supremum of linear functions. Okay, and that will be important. So so if f is convex, precisely what we have is that use of a maximal equation that has the property that at every point the function u is a super solution of all possible of all these equations, and a solution of a particular one. Okay, and so this is true for any function, convex function f of the square of u. Okay, so what are the basic properties we want to have about f? For basic properties is that you want f to be so here we are not variational. Here we are, all our tools are comparison principle and barriers. Okay, this is all we have. Okay, Therefore, what do we need to have comparison theorems and barriers? What you need is that, so the first thing you need is that F be monotone in the matrices, right? In other words, the Laplacian, right? In the Laplacian, if you have a solution and you add to it a positive quadratic polynomial, then it has to be a sub-solution, right? Because it's the Laplacian of a convex function is positive. So basically, the first thing we want to represent the Laplacian, to have comparison theorems, right, is that you want F to have the property that if you have M and you add to M a positive matrix, then F of M plus N has to be bigger than F of M. Okay, so that will make it elliptic, right? If I add that this is that this gain is proportional to N, that makes it a strictly elliptic, right? And bounded, okay, and bounded coefficients in some sense. Okay, so this is the first thing you ask for your F, is this monotonicity in N. In particular, if you have two matrices which are, or two D squares, right, which lie in the solution surface, that is, they satisfies that F of M, these M's are going to be D squares of U at the end, right? We are talking of F of D square of U, right? So if you have two M's that lie in the surface, right, then if you go from one to the other, right, then you go, if I want to go, you have this level surface F. So we have the equation F equal to 0, where this F is this level surface, right? And I have two matrices that lie in the solution surface, right? And I want to go from M to M, M1 to M2, right? Then what I can do is to M1, I add the positive part of M2 minus M1, right? And then I add the negative part of M2 minus M1, okay? And so, then if you, since both at the end end up being 0, that means that the positive and the negative has to be proportional, because when I add the positive part, the F moves proportionally to its size, and when the negative part goes down proportionally. So have the important property is that for two matrices that lie on the 0 set, on the solution surface, then the positive and negative parts are comparables. Okay, in other words, if you have two harmonic functions, right, then the difference is a harmonic function, and so the positive and the negative part of the difference are comparable. Okay, what else? Too many things in the hand. Okay, let me take it. Get rid of this. Oh, I overshoot. Okay, let me give. Right? Okay, give me 5 minutes to finish the introduction of second order, and then this afternoon I do the general theory. So, a particular fact from there is that if you take the derivative in the direction of M, Fij, right, which is the linearized equation, then this is uniformly elliptic. Okay, and so basically the first, if we remember the Georgy's ideas, we go here and say, okay, what happens with first derivatives of my solution? If I take a first derivative of the equation, then I have this coefficient Fij at the square of U, that is the derivative at the square, right, times the Aij of the first derivative. And so we are again in the previous situation where this matrix is uniformly elliptic because of the structure of F, but we don't know any continuity at this time because the square of U will have any continuity. So we have a linear equation with bounded measurable coefficients, okay, and the first derivative satisfies that. And so what people try for many years to do is reproduce the Georgy idea and show that solutions with bounded measurable coefficients, non-divergence equations, their solutions satisfy a Harnack inequality. They are Helder continuous and satisfy a Harnack inequality. Okay. The other, so basically, the other thing I want to observe is that, here we are, if you show that the gradient is Helder continuous, we are very far to reaching Schauder estimates, right? Because the square of U is far below the gradient, right? So So if f is in fact in the lim sub case, the solutions don't have to be C2 or better. There are counterexamples, Dutton-Asdirashvili, for instance, that solutions are only C1 alpha. Okay. In this, so now if f happens to be convex, that is, if f is the supremum of a family of linear functions, then if you take second derivative, right? When you take the second derivative, you can put the two derivatives in the d square, and so you get an equation for the second derivative, and then, and if not, the other, when you take the second derivative, the other is to get gradient, right? So basically what you get is a positive matrix times a vector times the same vector. It's like when you do in the Laplacian and you get gradient u squared. Here instead of gradient u squared, you get gradient times this positive matrix. So this is vector, vector, positive matrix, this quantity is positive, which means that if we take it away, this quantity is negative. In other words, pure second derivatives are sub-solutions of equations with bounded measurable coefficients. Okay? And so basically the regularity theory for the second order equation goes like that. First there was so first Krylov and Safonov study look at equations with bounded measurable coefficients, and they show that, as the Georgy did, that those solutions of such an equation are Helder continuous. Okay? So that means that if you apply to the theory of fully nonlinear equations, that means that solutions of the Isaac equation are Helder because have a first derivative which is Helder continuous. Okay? And then the theory was complete the theory. So this is, as I said before, says you get C1 alpha regularity because the gradient is Helder continuous. And then came the theorems that Evans and Krylov separate the proofs in different contexts, that if f is convex, then the second derivatives are Helder continuous. Okay, and then you can apply the regularity, and depending on the f, you get higher and higher regularity. And the Evans-Krylov proof, in some sense, is based on the fact that all pure second derivatives are super solutions, but they all live in the same smooth surface of solutions, right? And so since they are super solutions, right, super solutions, when you go inside, they try to pull up, right? They have be bigger inside than the boundary. So all the pure second derivatives are trying to pull up, right? But since they are forced to be in this common surface, then they are getting they are being forced to oscillate less and less. Okay. So what I want to do this afternoon is to see more or less the similar theory, but for non-local equations. So thank you very much. Yeah.
So in the relation approach, the proof relies on sublet inequality, so it cannot be applied to integrable kernels.